first. And so, yeah, so hi, everyone. Thank you for coming today. We're pretty excited to restart the Theory of Computing for Fairness seminar series. Today, we have Jessica Sorrell as our speaker. So she is right now a PhD student at UC San Diego, where she's advised by Russell Pagliazzo and Daniele Micciancio. And she's been interested in responsible computing. She's been working on fairness and privacy, on robustness, on reproducibility. And also in the past, she has been working on cryptography and on secure computation. Also, in exciting news, she is going to be joining UPenn next semester, in which is going to be a postdoc with Aaron, who's right here today. And today, she's going to tell us about her work on reproducibility in machine learning. And so, yeah, take it away, Jess. Your turn.
Thank you very much. Yeah, thank you for the introduction, and congrats on getting both of my advisors' names right. That's very challenging, so well done.
Did I? I just improvised this, so.
Yeah, no, great job. So yes, so today I'm going to be talking about joint work with Russell, Rex, and Tony on reproducibility and learning. And this is work to appear in stock this year. Cool. So yeah, let's get started by talking, at least informally, about what reproducibility is and why we care about it. So here's a little character of the scientific process featuring guinea pigs. So a researcher, let's say, has a hypothesis that they like to test. Say they want to tell whether drug A is an effective treatment for disease B, right? And they design and execute an experiment over here in their lab to make empirical observations about the effect of drug A on disease B. So then they will analyze the results of their experiment, perform some sort of statistical inference to make conclusions about the original hypothesis. And finally, they'll summarize these findings and report them to the broader scientific community. So this is sort of like roughly how we like to imagine the scientific process working. So ideally, published scientific findings actually capture some sort of enduring real-world phenomenon. So in our example here, if the scientist reports that drug A does in fact have a significant effect on disease B, this effect should be reproducible, right? It should be the case that if another team of scientists were to follow the same experimental procedure that was written up in our report, that they would get the same results. Right, so this is very informally what we mean by reproducibility. Right? We want to be able to perform an experiment, summarize it, someone else can read our summary, get the same results from the same experimental procedure. Cool. So, but as many of you are likely aware, not all is well with reproducibility in the sciences at the moment. So there's this really interesting and kind of, I don't know, dismal survey published in Nature in 2016 that showed that most scientists from the disciplines that they surveyed, including chemistry, biology, physics, medicine, earth sciences, and other miscellaneous disciplines, had failed to reproduce experiments, right? So that's like the red bar here. So over 50% of scientists have failed to reproduce experiments. And maybe even more alarmingly, about 50% have failed to reproduce their own experiments, right? So this is like, best case, you think you'd be able to do the same thing you did twice, but it's, yeah, doesn't always work out that way. So concerns regarding reproducibility also extend to other sciences, right? And into the computational sciences, our sciences. So here we're going to be interested in machine learning. And this is reflected both in the literature and also at major conferences. So I think like ICLR and other conferences have started holding workshops and competitions around reproducibility, as well as sort of issuing best practices, guidelines, standards to make sure that results or like the papers that are submitted to these conferences are reproducible, or like at least have the aim of promoting reproducibility. So one obstacle to reproducibility in learning, right? So we might wonder, why is this even a problem? Like, we're writing code at the end of the day, like this should be sort of deterministic. Where's the failure of reproducibility coming in? And they come in all sorts of places. So one is it can be hard to actually track all the randomness used during like, say, training of a machine learning model. So like the initial weights of nodes in a neural network, for instance, those are things that are chosen randomly and can affect the results of training. That needs to be recorded so that if you want to be able to reproduce the exact same model. yeah, so that's also a question of, is code open source, right? Often code is proprietary. People don't want to share it for various reasons. And so this is going to, make reproducibility difficult. It might be disparate access to computing resources, right? So large industrial labs are going to have access to much greater computing power than our like academic research labs. So it might simply be like computationally infeasible to reproduce the experiment of one of these larger labs. There's also the issue with proprietary or closed off data sets, right? So if a research group at Facebook or Google, or like maybe a medical center trains a model on customer and patient data, there are like very legitimate privacy concerns that may prevent researchers from making their data sets public. And there's also issues of statistical flukes in training data. So even if a sample, right, is drawn IID from some sort of distribution, even in like this ideal scenario, it could just be the case that your data is like very lucky or unlucky in some way in terms of leading to you concluding a particular result, or like rejecting or failing to reject a null hypothesis. These statistical flukes do occur. So what do we do about this, right? We know that replication is a serious issue. We have some ideas about what may cause an experimental result to fail to reproduce, but we don't really have good formal definitions of reproducibility, right? We just have this informal expectation that, okay, well, if I follow your report, I should get the same thing you got. Okay? And without clear definitions, we can't really have a well-developed theory of reproducibility. So our work tries to start formalizing reproducibility to sort of the extent possible. And we're not going to solve all of these problems here. We're not going to solve the reproducibility crisis in this talk, but we're going to try to slice off a little piece of it, specifically the piece related to issues with statistical flukes in training data, and arguably to some extent privacy concerns. Right. So our notion of reproducibility is going to formalize replication under resampling of training data. So let's get into our actual definition. So yes, this is the definition that we introduced in our paper. And it's meant to capture reproducibility for specifically randomized algorithms, informally requiring that an algorithm should output the same result with high probability if its randomness is held fixed and its input data set is resampled from the same underlying distribution. Notably, we don't have any constraints on the underlying distribution D. It can be extremely poorly behaved, right? We don't need to make any assumptions on D. We just want it to be the case that if I give my algorithm 2 samples from this distribution and I fix the randomness between these runs, I should get the same output with high probability. Okay. I want to make a couple notes, I guess, about this definition and its introduction. So sort of there's other simultaneous work from people at Google. But first, this definition was inspired by the definition of pseudo-deterministic algorithms and work of Grossman and Liu and Goldreich. So in their case, they're saying, okay, for all X, it should be the case that most random strings will like map that input X to the same output. So this is sort of a similar flavor, but notably, we're saying sort of most samples, if you fix the randomness, then most samples should map to the same output. So there's sort of questions, like there's a difference in what you know about the distribution and what's being held fixed and what's being re-randomized. So this is, as I said, independently studied and introduced by Badi Ravi and Passon at Google. So they call their version of this definition, which is like a little bit different. They sort of break out our row parameter here into 2 separate parameters, looking at the probability over the randomness and the probability over samples. And they call this pseudo global stability, inspired by other related work by Mark Roy and Shai, where they study global stability in the context of differential privacy. So global stability sort of ignores this randomness here and just says that, okay, an algorithm is globally stable if you have some sort of high probability output for that algorithm over all inputs. Cool, so that's related work, and I hope I've represented it well here. So I guess before we move on, I do want to do like a quick comprehension quiz, because really the rest of our talk is going to focus on this definition. Oh, it looks like I have questions in the chat. So before we do the quiz, I guess, should I Okay, Aaron's already answered the question. Yeah, thanks, sorry. In this definition here, R represents the internal randomness to the algorithm. Okay, so moving on to our comprehension quiz to make sure that we're all on the same page about what reproducibility is asking for. Say I want to design a reproducible algorithm for some problem, any problem. How can I make a reproducible algorithm with parameter rho equals 0 if I don't care about utility at all? It doesn't have to be a good algorithm. It just needs to be defined. So what could I do?
You could just output a constant always.
Exactly, yeah. So I can just output the constant function. It will have garbage utility, but it will be 0 reproducible. Okay, now to be a little bit more subtle here and sort of get a, exactly what our definition is asking for. What if I don't want it to be the constant function? Is there anything else simple I could do? Again, I don't care about utility, but I don't want to always be identically 0.
You could output R.
Yes, okay, exactly. So I could output R instead. I can output my internal randomness. And then again, I'll give the same output for, once I fix the randomness, but I'll give different outputs for different random strings. Cool. All right, so everyone knows what's going on, so we can move on with the talk. That's permissible. So despite the strong guarantees of reproducibility, we can actually obtain efficient algorithms for a number of interesting problems. In this talk, we'll show efficient algorithms for reproducibly simulating statistical query oracles, so identifying heavy hitters of a distribution, computing the approximate median of a distribution, and pack learning large margin half spaces. Briefly, we might not have time to get into this, but you should at least be able to touch on it. So let's get right into statistical queries. How are we going to answer statistical queries reproducibly? So this model was introduced by Mike Kearns in '93 to sort of capture the problem of learning under a kind of label noise known as random classification noise. And in this model, sort of significantly for us, the learner will not get direct access to labeled data, but it will get statistics about the underlying distribution. So it can query its oracle for statistical information about the distribution. So here we have our analyst, and our analyst is going to submit a query to the oracle, and the oracle will answer with the expectation of that query over the distribution to within some tolerance tau, right? So it's allowed to be a little bit off. Great. So unfortunately, grudgingly, at the end of the day, we all have to acknowledge that like oracles aren't real. And so to realize a statistical query oracle, what we typically do is we draw some sample from the underlying distribution, and we use this sample to empirically estimate the expectation of the query on our distribution. Right? And we can just take our sample large enough to use concentration bounds to argue that we'll be within tau of the expectation. Cool. Now let's get into making these things reproducible. All right, so what is the problem with the previous approach where we just drew a sample and empirically estimated the value of our query? Why is this not reproducible? And to see that, I sort of like laid out the 0-1 interval here, which is the domain for the answers to our queries. And let's say that like the true expectation of our query is this green dot here, right? So it sits right here, and we're going to estimate it using sample S1. So some samples, like the sample, will lead to an underestimate of our expectation. Another sample might lead to an overestimate. So there's this 2 tau interval that our answers can fall in, and right, we aren't guaranteed any kind of reproducibility because our different samples will lead to different estimations. So to fix this, we're going to try to find canonical representatives for different values in the 0-1 interval. So what we're first going to do is we're going to partition this 0-1 interval into subintervals of width alpha. And then we'll take the midpoint of each of these subintervals, and these will be as sort of canonical representatives. So in the case we were looking at just a second ago, both the underestimate and the overestimate that we got from our samples will fall in the same subinterval. And so they'll both, we'll map both of these values to P4 here, and our algorithm will return P4 rather than returning the empirical estimate itself, right? So here we're reproducible because both values get mapped to the same representative, but we're not done, right? So what if the true value of our query lies like on the boundary two of these subintervals, then we have the same problem where an underestimate will lead to us returning P3 and overestimate will lead to us returning P4. We're not reproducible. What do we do? So note that we haven't used our random string anywhere here yet. And so that's the next step in making things reproducible. We're going to randomly pick the starting offset for these subintervals. Okay, so different randomness will lead to different partitions, will lead to different midpoints. So here we can see a couple. This one's good for reproducibility in our case. This one's not so great. Again, our different estimates fall on different sides of the boundaries. And again, we have another bad one, but we can see that as we use different randomness, we have different boundaries for the interval. And so now we can bound reproducibility as the ratio between the 2 tau, and here 2 tau 0, I guess, region in which our estimate lies, over the alpha possible, like the alpha width region from which we're picking our starting offset. So if we always pick our offset to start from some value like less than alpha, then there's this like alpha range of values that we could have started from. 2 tau 0 of them are going to be bad for reproducibility, and so we're 2 tau 0 over alpha reproducible. And notably, will be about alpha accurate in the answers that we return to our statistical queries here, because most of the error is going to come from the fact that we return a midpoint, right? So if we have some estimate here, we have some error from using this empirical estimate, but then we're also dragging our estimate to the midpoint of whatever interval, and that's going to change the value by about alpha over 2, or most alpha over 2. So this means that if we take tau 0, the tolerance for our empirical estimate, to be about on the order our reproducibility parameter times our target tolerance parameter, then we end up with a reproducible and tau accurate statistical query oracle. So that's statistical queries. Here's a slightly more precise theorem statement where we actually count for failure probability of our estimates. But are there any questions about this? This is sort of this like randomized rounding that we use to answer statistical queries is kind of the one weird trick that underlies most of our reproducibility techniques. And so if there are questions about how or why this works, I'd love to take care of them now.
Will you say anything about answering large numbers of statistical queries?
I will not. Unfortunately, we at the moment don't know how to do anything better than just like union bounding over all of them.
Cool, thanks.
Yeah. I would love to have more to say about that. Cool. So,
in the previous example, I'm reproducible if I get the exact same answer for each run. Okay.
Exactly, yeah. So it's like a really strong stability requirement. More questions? Great. Okay, so now we're going to move on to heavy hitters problem. I'm trying to pull up my notes. So let me first define this. We'll say that D is a distribution over domain X, and we'll say that some element of X is a V heavy hitter of our distribution if it's the case that D assigns probability at least V to X. So to give an example, let's say these X1 through X5 are the support of some distribution D, and this histogram just representing the probability. X4 and X5 here would be quarter heavy hitters, 1/4 heavy hitters of D, and the rest of the elements would not be. And this problem comes up in applications like search engines, recommender systems, places where you want to track very frequent queries, or commonly, you could be like commonly purchased items, things like this. And we give a reproducible algorithm for identifying not exactly V heavy hitters, but epsilon approximate V heavy hitters of a distribution. And that's using a sample that's going to be quadratic or inverse quadratic in the reproducibility parameter. Well, so this is going to use sort of similar techniques to our statistical query algorithm. So I'm going to go through this a little bit faster maybe. The idea is that we're going to start by drawing a sample from our distribution that's large enough that we're guaranteed that all V heavy hitters are contained in that first sample with good probability. Then we're going to use a second sample to estimate the probability of each of our candidate heavy hitters under the distribution D to within good accuracy. And then we're just going to, get rid of everything from our list of candidate heavy hitters that isn't actually a heavy hitter. But we're going to do this to make this reproducible. We have to account for the same problem that we have with statistical queries. What if the true probability of an element in D, under D, is very, very close to V? Then when we use the second sample to estimate that probability, sometimes we'll underestimate it, we'll remove it from our list of candidate heavy hitters, sometimes we'll overestimate it and it'll get included. And so our list of heavy hitters won't be reproducible. So we're going to introduce a little bit of noise into the actual value of V by randomly picking a V prime uniformly at random from V minus epsilon, V plus epsilon. And now we can argue, okay, well, whatever the true probability of an element under, of an element in X under D, the chances that our value V prime got too close to the true probability, such that the error from our empirical estimate matters, is going to be low. We can bound this. And so this is, very much like the statistical query case where we randomized our boundaries to say that the probability of boundary hit a problematic region for us was small. Oh, and so now that we've removed everything with probability less than V prime from our candidate heavy hitter list, we'll just return the list that remains. And that brings us to approximate median, right? So I wanted to cover these first two algorithms because we'll be using them as subroutines here. And a tau approximate median for distribution D is going to be any sort of element where the probability of being less than or equal to that element is at least a half minus tau, and the probability of being greater than or equal to that element is at least a half minus tau. So this is a pretty fundamental statistical task that we might naturally care about. But in the context of reproducibility, it has an additional application, which is that it will let us generically convert a non-reproducible algorithm into a reproducible one. So long as the algorithm has codamine in the reals, right? So if we output a real number in some bounded interval, then we can use the following approach to make this algorithm reproducible. So here's A, our non-reproducible algorithm. And we're going to run it a whole bunch of times on samples S1 through Sn coming from our distribution. Okay, so we're going to get a whole bunch of outputs of A. And we're going to treat these outputs as a sample, right? So what is it a sample from? It's a sample from the distribution over outputs of A induced by sampling from our original underlying distribution. And we'll feed this sample to our reproducible median algorithm, right? So now we're going to get reproducibly a median from the distribution over outputs of A. And then there'll be a little bit of finessing in terms of arguing correctness, right? Because if A has any failure probability, we'll have to be careful about managing that. But we will reproducibly select a value from this distribution over outputs of A. So now that we know why we might care about reproducibly approximating medians, let's get into our actual algorithm. And for those of you who are familiar with the privacy literature, and so know Bund, Stemmer, and Vedon's algorithm for DP interior point, or the follow-up work by Kaplan, Lichitman, Sorrell, now and Stemmer, what we do is going to look sort of similar to that, except reproducibly favored. Also, for simplicity, we're coming with approximate medians here, and we're just going to let tau be a constant, specifically 1/16, because that's going to make things a little bit simpler for us. And we'll denote our domain as the binary strings of length D. And so to solve this approximate median problem for distribution D, we're going to reduce to finding a worse median, sort of garbage median for another distribution. And much like the diagram I just showed, it's going to be the distribution over tau approximate medians for D that are produced by some sort of non-reproducible median algorithm, right? So if we go back to our picture here, we can imagine A is just a generic median algorithm. And so D prime here is going to be the distribution over outputs of such an algorithm generated, induced by sampling from the distribution we actually care about, D. So note that because D prime is a distribution over tau approximate medians of D, that we can return a kind of garbage median for D prime and still satisfy the problem, right? Still solve the problem that we aimed to solve, which is finding a tau approximate median for D. It's kind of a looser approximation factor. Our setup here, again, similar to the DP interior point algorithm, is going to be a binary tree over where like all of the leaves are elements of our domain X, and all of the internal nodes are going to be labeled by prefixes of elements of X. And the weight of an internal node will be the probability under D prime. Again, this is the distribution over approximate medians. So the probability that an X sampled from D prime has the prefix associated with the node, right? Has the label of the node as a prefix. Cool. So I claim that to solve our approximate median problem over D prime, we want to find one of two things. Okay, so we either want to find a 1/4 heavy hitter of D prime. And why is that the case? So note that like all of the elements in support of D prime are leaves of this tree here. So if we run our heavy hitter algorithm and find on the leaves, and we find a good heavy hitter under D prime, then we can just return this as an approximate median, right? We're going to be happy with like a garbage approximate median of D prime, and so that suffices to solve our problem. But we're not guaranteed that such a heavy hitter exists, right? Maybe D prime doesn't assign probability at least 1/4 to any particular element of its support. So if that's the case, then we'll be happy as long as we can find a prefix S, some sort of internal node of our tree of length L, such that if we restrict elements in the support of D prime to their first L bits, that they'll match S with probability between 1/4 and 3/4, right? So we know such a node must exist because we know, first of all, we know that no particular leaf here has probability greater than 1/4. And we know that if we start at the root, right, that has probability 0. Or probability 1 rather. So there's got to be some sort of node on the way down to the leaves that has this intermediate probability that has weight between 1/4 and 3/4. And why do we want such a node, right? Like, how does this help us with our goal of finding an approximate median? And the answer is that the label, the prefix associated with that internal node, is going to give us the prefix of a good approximate median. So in this case, either if S is the prefix, then if we pad it out with zeros, either that will be a good approximate median, or if that's not the case, then S padded out with ones will be. So let's imagine this line here is like an ordering of elements of X. Then because we know that the probability that D prime assigns probability no more than 3/4 to elements between S0 and S1, because it assigns no more than probability 3/4 to this prefix, we know that there's got to, like, the remaining 1/4 of the mass has to go somewhere, right? So there has to be at least an 1/8 less than S0, or at least an 1/8 greater than S1. So we can return S0 if it's the case that there's enough mass on elements like less than it, or S1 otherwise. Cool. So we've now reduced to finding this sort of intermediate weight node of our tree. So how do we solve this problem? And the answer is further reducing the problem. So we're now going to reduce to finding an approximate median of yet another distribution. And this distribution we're going to call D double prime. So D double prime is the distribution induced by sampling 2 elements from D prime and then returning the length of the longest prefix on which they agree. So let's say X1 is 1100 and X2 is 1000, then I would return the value 1 because they both agree on a prefix of length 1, but they don't agree on a longer prefix. Right. So note that D double prime, this new distribution that we're considering, has domain size smaller than, or no greater than log of our original domain size. So we're over a much smaller domain because we're looking at prefix lengths. Cool. So we now reduce to finding a tau approximate median for d double prime. And note that this is going to give us a recursive algorithm. So here's our tree again. How can I use a approximate median from d double prime to help me find a high weight node in this tree for d prime? So I claim that if I get L back as my approximate median for d double prime, that means I can restrict my search for high weight nodes to nodes at level L or level L plus 1. So between these two levels, there has to be a good node that satisfies what we're looking for. So let me argue this claim. So there's going to definitely be a node at level L that has probability at least a quarter. And that's just going to follow from the fact that L is a tau approximate median of d double prime. But we don't know that there's going to be a node with weight less than 3/4, right? It could be the case that there's only a node with weight 1 or something like that. So in this case, at level L plus 1, one of the two children of node V has to have mass less than 3/4. Why is that? So if it weren't the case, if both of them, or like if at least one, I guess, had probability greater than 3/4, then the probability of sampling an element from d double prime, or rather sampling two elements from d double prime that agree on a prefix of length strictly greater than L would be too large, right? So if we have probability of sampling an element with prefix S with probability greater than 3/4, then the probability of sampling two such elements, right, is going to be 9/16. And this is going to be too much probability mass, right? We said that L was a 1/16 approximate median for d double prime. And so this is going to contradict the fact that L is such an approximate median. So this means that we can just restrict our search to level L and level L plus 1 of our tree. And so now we're going to search these levels again using our heavy hitters algorithm, so our reproducible heavy hitters algorithm, because again we have to do this reproducibly somehow. So we can consider the distribution of elements sampled from d prime restricted to their first L bits, and then the distribution elements sampled from d prime restricted to their first L plus 1 bits, and run heavy hitters on these two distributions to find the node that we were looking for. So great, we get a good node with weight between 1/4 and 3/4, and that's from using our recursive call to the approximate median algorithm. And then we said that we could use that we were using our heavy hitters algorithm to find this, and we can use our So I forgot that we have to also use statistical queries to weed out elements that have too great a probability. But then we have our good prefix, and then we can again use reproducible statistical queries to check which of S0 and S1 here make a good approximate median. So great, we have now solved our problem recursively. And the question remains, what is the sample complexity for this algorithm, right? This is doing some funky stuff. And we'll note that because we're reducing our domain size to log of the previous domain size at each step, that we can make at most log star recursive calls, right? So we'll hit our base case after log star size of domain recursive calls. And at each step of the algorithm, all right, we have to run this. We generate samples by running a non-reproducible approximate median algorithm on the input distribution. And so we're going to end up with this gorgeous sample complexity here, where we have an exponential dependence on log star of the domain size, but we again only have inverse quadratic dependence on the reproducibility parameter, where this like 3/tau² base for the log star is coming from the fact that we have to run this approximate median algorithm to generate a sample for the next level of recursion. So this isn't ideal, right? So there's, like I mentioned, our techniques are sort of similar to interior point or private interior point algorithms. And the first iteration does have this exponential dependence on log star of the domain size, but the follow-up work is able to bring this down to, like polylog star in the domain size. And so we'd like to be able to do that. We don't quite know how yet, but I definitely believe it's possible, and I do think it's sort of the right answer. Well, so I guess before I move on to half spaces, are there any questions about the approximate median algorithm? Nope. Okay. So I will now move on to reproducibly learning half spaces. So this slide is just going to go over the PAC framework real quick. If you already know and love it, feel free to space out for a second. So we'll say a concept class C is going to be some sort of set of functions. This will be the class that we're interested in learning. And we're interested in functions here that map their inputs to ±1. So we have binary labeled data. F is going to be some sort of function from our concept class. D will be an unknown distribution over labeled examples with marginal D sub X. So this is the marginal over just sort of like the input data. And the data points here will be labeled by the function F. Right? So D is supported by elements F of X. Or, yeah, X, F of X. And we'll say that an algorithm A is a PAC learner for our concept class D if it's the case that for all epsilon delta parameters, we have that A outputs a hypothesis that is probably approximately correct for our target function. So the probably part of this is over samples from D. So it should be the case that probably our algorithm A puts a hypothesis with good utility. For our target function. And then the utility portion, like what does it mean to have good utility? And it means that you're going to be approximately correct on F, which means if I sample elements X from this marginal distribution dx, that our output hypothesis should agree with F of X with probability at least 1 minus epsilon. Great, so we are going to reproducibly PAC learn half spaces, specifically half spaces with large margin. This is going to be a critical assumption for us. So here our concept class C that we're aiming to learn is a set of functions. So it's going to be the set of functions defined by a unit vector W. Here we go. So yeah, we'll be interested in learning functions of this form indexed by a unit vector W that on input X will output the sign of the inner product of W and the input data. So notably, this means that there's some sort of hyperplane that separates our data into negative and positive examples. And our large margin assumption is assuming that there's some sort of bound tau where the distance between elements in the support of our marginal distribution dx and the true hyperplane will be bounded by tau. So everything, I should say, like the data doesn't get too close to the boundary between positive and negative examples. And the way that we're going to reproducibly learn half spaces is by using a boosting algorithm, specifically the smooth boosting algorithm of Sorrell. So a boosting algorithm will take a weak learner, where a weak learner, rather than having very good agreement with the target function on the underlying distribution, will only give you classification rate better or accuracy about like gamma better than a coin flip, right? So it's definitely better than random, and it's bounded away from random by some constant gamma, but it's not great, right? It doesn't suffice to satisfy our definition of PAC learning. And we show how to reproducibly run Sorrell's smooth boosting algorithm along with this reproducible weak learner to boost the weak learner's accuracy to something arbitrary and therefore satisfying our PAC definition. Unfortunately, this is going to require poly D samples, where D is the dimension of the half space that we're learning. But we are a polynomial in all of the other relevant parameters too, right? So 1/tau, where tau is this margin parameter, 1/epsilon, our target accuracy, and 1/rho, our target reproducibility. But typically we would like to be dimension independent, and there are, again, private algorithms for learning half spaces that are independent of dimension. And it seems like we should be able to match that. We have some ideas for how to get there though. Great, so yeah, I guess I'll just now go into ongoing and future work that I'm pretty excited about. So we've added somebody to our crew here. So we're now also working with Max Hopkins, who's also at UCSD, and everyone else you saw from the title slide. And one thing that we're really excited about and working on is a connection to differential privacy, right? So right now we have tentative results, and I'd like to emphasize that everything on this slide is going to be very tentative, not completely written down, and also ordered roughly in descending order of us knowing what we're talking about. But yeah, so we have sort of tentative connections to privacy, and that we think we can show that pure differential privacy implies there exists a reproducible algorithm for the same problem, and reproducible algorithm implies the existence of an approximately private algorithm, where notably all of these are sample efficient. The reproducibility to approximate DP connection is computationally efficient, but the pure DP to reproducibility connection is not computationally efficient necessarily yet. We're also working on finding connections to pack learning. So we have reproducible pack learning of finite hypothesis classes, and also agnostic learning for these finite hypothesis classes. We'd also like, as I mentioned before, to find better median and half space algorithms that end up with sample complexity that's sort of comparable to their differentially private counterparts. And also we'd like to find a reproducible parity algorithm, right? So we have this reproducible statistical query algorithm, which covers like a whole broad class of problems that you might want to, problems in pack learning, but it notably doesn't capture parities. And so we're working on sort of, getting that piece of the puzzle solved reproducibly as well. And at the beginning, I talked all about the replication crisis in the sciences, and then sort of proceeded to not say very much about science at all for the rest of the talk, and mostly focus on standard problems in machine learning theory. But I'd really, really love to get back to sort of motivating question of reproducibility in the sciences, and notably looking at reproducible hypothesis testing, right? So are there like sort of frequentist hypothesis tests where we can guarantee that whatever procedure you run to analyze your data will output reject null or fail to reject null with high probability, regardless of the sample data that you collected. And finally, because this is a fairness seminar, we talked a little bit very briefly about potential connections to individual fairness, not necessarily that the definition of the reproducibility gives any sort of immediate connections to fairness, but that the same techniques we use, sort of finding canonical representatives for values, could potentially be useful for individual fairness if we want to map similar individuals to similar outcomes. Great, so I guess I've ended a little bit early, so I have lots of time for questions. And yeah, be happy to talk more about any of this like future ongoing work or anything that came up during the talk.
Yeah, thanks a lot for the excellent talk. I don't know if other people have questions, but I guess I could just like start first. Yeah, so actually, can you say a bit more about kind of like this connection between differential privacy and here reproducibility? Sorry, it's hard to say. Yeah, no, actually, that just like sounds super interesting. Like, so can you like, is it just like, are you kind of like just trying to leverage kind of like the stability properties of privacy to actually get reproducibility here, or how does that work at a high level?
Yeah, so I didn't quite hear what you said. Like, sorry, leveraging the stability property, is that what you said?
Yes.
Yeah. So the pure DP to reproducibility result goes through sort of representation dimension, and the characterization of pure DP learning And also our reproducible pack learning for finite classes, right? So we're going to sort of get this cover of our hypothesis space, and then notably that's going to be finite. And then we'll show that we can reproducibly learn over our cover to get a reproducible algorithm. And then the next arrow, the reproducibility, and this is again like why it's not necessarily computationally efficient, right? So we have sample efficiency, but not necessarily, yeah, so we don't need to actually get labeled data. But then for the reproducibility to approximate DP connection, this is just going to be a sort of like subsample and aggregate type of technique, where right, reproducibility is going to mean that there's like a sort of high probability hypothesis. We are going to have to sort of boost reproducibility potentially of the starting algorithm to guarantee we preserve utility. But yeah, that's roughly how that goes.
Yeah, thanks a lot.
Yeah.
Hello, I have a very high level question. Have you thought about ways to interpret this in some kind of robustness adversarial framework where the non-reproducibility is maybe replaced with something of that nature?
Yeah, so this is actually, I didn't put it on the slide, but this is something that we have talked about as well, because it seems, again, like what we're discussing here are stability notions, right? And robustness is sort of another stability notion. One difficulty that we've had in, I mean, we haven't thought about it super hard, but one difficulty is sort of that comes up almost immediately is just matching the types of definitions. This problem also comes up with differential privacy, where in robustness, we're not saying anything about, if I have a perturbed sample, right, I'm not saying anything about the underlying distribution that it comes from, and then reproducibility is asking, okay, for two samples from the same distribution. Yeah, I think we just have to be, I guess there are also a bunch of notions of robustness. So, you know, we can maybe just pick the one that works. But yeah, there's been we didn't see anything that followed immediately, but we are interested in it. And sort of relatedly, another thing we really would like, as motivated by, you know, all the stuff I talked about at the beginning, is relaxing this requirement that we have two samples from the exact same distribution, right? Like this is great, and all sorts of results are possible making this assumption. But in the real world, where like IID samples aren't real, you're not going to get two samples from the same distribution unless like your data is algorithmically generated. So for actually reproducing a result, we might like to say something about, okay, you're drawing a sample, you know, from a population that's similar to the population that was used for the original result. So this is sort of maybe another notion of robustness under like distribution shift that we might care about as well. At least that I think is like exceedingly well motivated for like the problem that we're trying to address.
Thank you.
Does that answer your question?
Yeah, I think so.
Okay.
So I'd like to ask a question. After such a beautiful talk, I don't want to ask you something where you're going to have to say no, but I'm trying to understand. So one thing that comes up, say when you're trying to learn a half space, is that you don't have a perfect solution, and there are many choices of things that are equally good, and none of them is perfect. So does anything that you're doing help, or is it the case that the margins that you need, your margin requirement says no, you can't help in this situation?
So if there are many, so yeah, reproducibility still helps in this situation. I mean, again, like as long as your data satisfies the margin requirement, because again, like I guess like if you think about sort of what we're doing with reproducibly selecting a half space, we're sort of discretizing. I guess I didn't get into the weak learner, so that's probably, yeah, let me get into it a little bit. Our weak learner, you can think of it as discretizing RD, and then picking you know, like a representative from a good region. And so in this case, if there are many hypotheses that are compatible with your sample data, then again, as long as we're randomizing the discretion of RD, with high probability will get mapped to the same, two samples will map us to the same region. They won't map us to the same half space, but they'll map us to the same chunk of RD, and then we return the representative from that chunk of RD. There, yeah, I guess I sort of skipped over this, but maybe I'll use this as an excuse to talk a little bit more about our half spaces algorithm, where we actually give two weak learners that you can boost. One of which is essentially just like a, find the center of mass for distribution over samples, and then round that to some sort of like lattice point. And this gives a computationally efficient weak learner that unfortunately has like a I think like roughly d to the 4 sample complexity dependence, right? So that's a sort of like large polynomial dependence on the dimension of the half space, which is not great, but it's computationally efficient. But we're also able to use a cool like optimal foams result of Avi's and others that gives a much lower, closer to linear dependence on the dimension. Unfortunately, the foams construction runs in time exponential on the dimension. So if you have a lot of time, but you'd like to get away with fewer samples, there's this other weak learner that you can use as well. But yeah, so both of these weak learners, though, essentially give you a way of discretizing RD. So the foams construction gives you a particular discretization, and then our other one is a kind of coming up with like an integer lattice that you then round to, using a not necessarily good rounding algorithm, something kind of like Babai's algorithm rather than like a closest vector problem algorithm, which would of course be exponential time in the dimension also.
Okay, you just mentioned hypothesis testing as a future work. Can you say a bit more then?
Oh, about hypothesis testing?
Yeah.
Sure. I can tell you why we think this might be possible. So I guess if you, the closest thing that we've had to an idea for this so far is looking at trying to apply our reproducible median algorithm to distributions over p-values. So you can imagine running an experiment several times, generating statistics, and from these statistics generating p-values. And then under the null hypothesis, right, you would expect to see this sort of uniform distribution over p-values, right? So you know what the median is in this case. And then depending on what your alternate hypothesis is, you might be able to say something about, oh, the median of distribution of p-values under my alternate should be sufficiently different that I can distinguish these two using even just a reproducible approximate median algorithm. And so then if we have this reproducible approximate median algorithm, that means that we accept or that we reject or fail to reject with, with good probability because we use the reproducible median algorithm. But actually defining when this technique could work, right? Like what assumptions, like what problems it could be good for, is super open. There's just sort of like the first, like conversation we had about it.
Okay, Gareth, thank you.
I have a question. You mentioned looking at connections to individual fairness. Could you elaborate on the connections that you're looking at?
Oh yeah, so there's I think I maybe hopefully mentioned that these are put on the slide roughly in descending order of us knowing what we're talking about. So I think I actually did like fully exhaust what we have in terms of ideas. But again, I think the hope is that you could maybe use something again, like we wouldn't be trying to say you could use a reproducible learning algorithm to produce a fair predictor, but rather maybe use some of our randomized rounding ideas within like the algorithm itself to make sure that you output the same values for individuals that are close in some sense. That look like each other, but that's pretty much it. Like that's I think all we have so far.
Okay,
it's sort
thanks.
of like something that we've queued up that we want to look at. So if people have ideas, I would love to talk about them, but we don't. We haven't explored it yet.
I have a question there. Would it be learning the metric like reproducibly? So like you do a bunch of queries to like estimate the metric, kind of like the learning metric fairness paper from Fork 2020, and then if you do something in this vein, you can like be confident that your individual metric is like reliable because it's reproducible, and then you can have confidence in it, sort of.
I'm not sure. I would want to think about this before, but I'd be interested in chatting with you about this offline.
All right, everyone. It is 1 p.m. right now. So if we actually don't have any additional questions, we can probably stop here. But like, thanks again a lot, Jess, for the great talk. Like, thanks everyone for coming.
Thanks a lot.
Yeah, thanks for coming. It was a pleasure to join you all today.